Yes, so I will talk about aspects of analytical waveform modeling for comparable mass binary systems. And you will hear, of course, or you already heard earlier today, some aspects of it, and you will hear many more. But the plan is that I will tell you a bit or remind you a bit about the crucial role of models for detecting and especially interpreting gravitational wave signals from binaries. And one example of a current approach to compute full models that can be used for the data analysis. Specifically, I will tell you a bit about the effective one-body approach and explain a bit how we can include more physical effects in this framework. And then I will also give some remaining challenges and an outlook to the future prospects. So let's just remind ourselves that gravitational waves from binary systems are really the characteristic fingerprints of their source. For example, in blue on this slide, you see a typical waveform from a binary system of equal mass black holes on circular orbits, whose spins are aligned with the orbital angular momentum. And they undergo a slow inspiral, which accelerates due to gravitational radiation. Eventually they collide and merge, which is the peak in the gravitational wave amplitude. And then they form a final remnant black hole that is initially highly perturbed, but then settles down. And you see below some examples of how the waveforms can change if you have unequal masses or misaligned spins. And of course, there are many more examples. So the key role that all of these models or these theoretical calculations play is that in gravitational wave data analysis, we measure some signal, and then we would like to know what was the source of it. And this mapping between signal going backwards to the source properties is highly complicated because one has to solve for the dynamical space-time of the binary system. And this is described by the Einstein field equations in GR, so it's quite complicated. And of course, if one goes beyond this, it gets even more complex. So over the last decades, models have been developed both in analytical and in numerical relativity that enable doing an approximate mapping between source properties and gravitational wave signals. And then these models, for one example is shown in orange here, they can be used to cross-correlate with the data to interpret the measurements. So here, this is one example of the first discovery. The data is shown in blue. That was such a loud signal, it could be observed or detected just by conditioning the data. But then to know what was the source of this signal, we need a model to compare to. And clearly the model I'm showing here does not match the data quite well. But if we take a model with lower, for a binary system where the source had a lower total mass, then already we can match the phase of these oscillations quite well that are present in the data. But then the amplitude is still wrong, but that can be changed by adjusting the distance. Of course, here it is very simplified. In general, it's a 15 or even more dimensional parameter space over which this kind of fitting has to be performed. And in the actual data analysis, it's not just a point estimate, it's an actual Bayesian analysis with a Markov chain Monte Carlo exploration of the likelihood and so on. So for measuring the properties of each event, one requires millions of waveform evaluations for this data analysis. And furthermore, something I did not mention explicitly here, but waveform models are also essential to detect signals by matched filtering, where there's a bank of pre-computed model waveforms that are cross-correlated with the data to filter out a weak signal that might be buried in the noise. So as I mentioned, the computing such models is actually a significant theoretical challenge, even if one considers just GR in quotation marks and black holes, because one has to solve for the dynamical space-time, which is a very complicated task. But there are different approaches to computing waveforms in different regimes of the parameter space of the binary system. So this is shown here schematically in terms of the orbital separation on the y-axis and the mass ratio on the x-axis. So as one goes down in the plot, the system gets more relativistic. And we have two exact cases in Newtonian dynamics at infinite separation. Yeah, the two-body problem can be solved quite straightforwardly. We also have an exact solution in the test particle limit, which is valid for infinite mass ratio, where there's a test particle orbiting a black hole. But for merging binary systems of comparable masses, we are mainly interested in not too high mass ratios, but also strong field regimes near the merger. And for that, the only way to really probe the fully nonlinear strong fields is to do numerical relativity. So this you will hear more about in the talk by Harald Pfeiffer. But this is currently the only approach that gives access to the really strong field regime where everything is highly nonlinear near the merger. But it is also computationally very expensive to compute a waveform. So the simulations are currently limited due to the enormous computational cost and also challenges with resolving different scales in the simulation to not too extreme mass ratios and not too large orbital separations. So clearly we also need to fill in other parts in this parameter space. And to do that, we have to think of different approaches. And these are done by performing analytical approximations. And the idea of analytical approximations is to consider the different scales involved in the system, for example, when one has a binary system at large orbital separation. Or for another example is a binary system at large mass ratio or so. And then one divides up the space-time into different patches. And in each patch, one can perform a different approximation that is only valid in some limited regime, but then it can be matched to a different approximation in a different patch of the space-time. So that in the end, one can describe the system through a tapestry of approximation schemes. And to do that, one has to identify also characteristic dimensionless parameters that can be used for perturbative expansions. And that again depends on the kind of system you want to consider. You could, for example, consider that the size of the object compared to the orbit when the two objects are far apart is quite small. So you do a perturbative expansion in that parameter and so on. And in this conference, you're going to hear more, for example, about post-Newtonian approximations, which are one example of exploiting these parameters for perturbative expansions, or about gravitational self-force calculations, which are another example. And so these methods can be used to fill in the description of the two-body problem in larger parts of the parameter space here. So as I mentioned, we have post-Newtonian theory pushing for any mass ratio more towards a strong field regime. On the other perpendicular regime, we have gravitational self-force calculations pushing away from the test particle limit more towards comparable masses. And another approach that is also becoming very popular in recent years is post-Minkowski scattering calculations, which are kind of not so easy to indicate on this diagram, but they also give a lot of interesting information on the two-body problem, because they consider unbound systems, whereas here the diagram is focusing on bound system binaries, but still even from the unbound calculations one can gain useful information. So now we've filled in with perturbative methods, but these in themselves are also not yet enough, because we would, especially for comparable masses, describe the entire path of a binary system to merger through the entire stages of its evolution. So we need an additional method. And for this, we don't have a first principles scheme, but there are additional approximation methods. One is called the effective one-body model, which I will describe a bit more later in this talk, that combines all of the available information on the relativistic two-body problem into a single framework with the aim of computing complete waveform models that can be used for data analysis. So I will describe more about this later, but the basic idea is to map the phase space of the two-body dynamics onto the phase space of a simpler problem where there's an effective particle moving in some effective space-time. And this model has a Hamiltonian to describe the dynamics, then a mechanism to describe gravitational waves and the back reaction on the orbit, and then a connection to the merger ring down epoch of a binary system. There's also another approach that combines information, which is called the phenomenological models or phenom models, which aim at producing efficient frequency domain waveforms, although there's also some recent work available for time domain waveforms. So let's now discuss a bit more about the effective one-body idea. So to start with, in Newtonian dynamics, when we want to solve a two-body problem, we automatically already make an effective one-body approach, because we would go to the center of mass frame and describe the dynamics by the motion of the reduced mass moving in the field of the total mass, plus some trivial center of mass motion. So this idea is, we would like now to have some relativistic generalization of this kind of idea. And so the relativistic analog of a one-body system moving in the field of an other body would be a test particle in, say, for simplicity, Schwarzschild space-time. So in that case, let's say we have a particle of mass little m orbiting in the field of a black hole of mass big M, and we can write down the metric and construct the Hamiltonian for the motion of this particle in the 8-dimensional phase space from the inverse metric and the momenta. And for time-like geodesics, this Hamiltonian, it has a conserved value of -1/2 the mass squared. But it corresponds to the evolution parameter being the proper time of the geodesic. So that is not a very convenient quantity because it is tied to each geodesic. So we would like instead to have a global time evolution parameter. So we convert to coordinate time by doing a phase space reduction to a 6-dimensional phase space. So in practice, this can be done also by solving for eliminating the time momentum in, solving this Hamiltonian equals the conserved value for the energy or the geodesic Hamiltonian conjugate to coordinate time, which then acquires this kind of square root form. But now, okay, this is just for a particle in Schwarzschild space-time. How do we now apply this to describe a comparable mass two-body system? And the idea is that we take this particle in Schwarzschild as kind of a relativistic baseline or skeleton of the model, and we make some small corrections to it to include finite mass ratio effects. And these finite mass ratio effects are chosen to match post-Newtonian results, so that the model becomes exact in the limits of infinite mass ratio and large orbital separation. And in between, it is not exact. It makes some interpolation. Now, to make more concretely an identification between the two-body system and this effective problem we want to consider, we have to now think about how can we make such an identification in an invariant way. And this is done by considering the phase space areas or volumes measured by the action variables, which are invariants of the system, and requiring that those are equivalent between these two different systems, because that then kind of ensures that the phase space dynamics are identified in this way. And doing that, one can solve for how the constants of motion, like the in the absence of radiation, the angular momentum and the energy are related between these two descriptions. So on the one hand, we have, for example, an effective energy, which is the energy of the, in this effective description, but it is related to the two-body energy, E, by some more complicated formula involving also the masses. Now, such a relation you might have seen before if you study Feynman diagrams, because it also arises in other contexts. For example, in scattering calculations, one gets a similar identification, and also initially such an idea of effective on-body inspiration came from a similar problem in quantum electrodynamics, which required solving for bound states of positronium, which is an electron and a positron system. So it's very relativistic in the sense of special relativity, but it's much easier to solve a system where there's an electron orbiting a positive charge, which is the hydrogen atom. So they already proposed in 1970 a similar idea to make a mapping between these two systems. So having identified the energies, or equivalently Hamiltonians, then one can finally write down what is the two-body Hamiltonian, how does it relate to the effective Hamiltonian, and now there's some square root relation that came in because of this squared relation solving for E of E effective. Okay, and the interesting thing now is that already we can identify that the mass in this effective space-time has to be equal to the total mass of the system, of the two-body system, and the mass of the particle has to be the reduced mass as in the Newtonian limit. And the parameter that characterizes deviations from the test particle picture is the symmetric mass ratio, mu, which is the reduced divided by the total mass, and it ranges from 0 for a test particle to 1/4 for equal masses. So it's not exactly a small parameter, but it's also not huge. That's already interesting to note. Now, let's just recap what we have derived so far. So we have in the two-body EOB Hamiltonian, given in terms of an effective Hamiltonian, which is analogous to Schwarzschild's test particle case. But instead of having just the Schwarzschild potentials, there are now corrections that depend on the mass ratio, or more precisely, the symmetric mass ratio. But and this system recovers exactly the second post-Newtonian dynamics. Now, in post-Newtonian theory, if you compute a Hamiltonian up to second post-Newtonian order, you get this entire page of expressions. So all of these you have to add together to get the second post-Newtonian result. But in the effective on-body, all that has changed is just a Schwarzschild test particle plus one correction term to the potentials. So this is already really powerful, because even irrespective of how realistic this model is ultimately, it already is a quite efficient way to summarize information from post-Newtonian theory, because the entire page here gets to reduce to just one extra coefficient in each of the potentials. But it doesn't remain so beautiful at higher post-Newtonian orders. One needs some non-geodesic terms and more terms in the potentials, which are then also resummed instead of having this kind of series expansion in 1 over r and so on. So one has to do a bit more manipulations and also include some extra terms that parameterize unknown post-Newtonian coefficients with some free coefficients that are calibrated to numerical relativity. So that describes the dynamics, but then there's also, given the dynamics, one can compute the radiation, and the way it is done in EOB is also, again, instead of taking the post-Newtonian results, which are some long expansion, the terms are resummed into different factorized coefficients here. For example, in blue here, I've shown in the post-Newtonian results some tail effects, which also appear again and again at higher orders. These are all summarized in one factor here. And similarly, these black terms, which are also some post-Newtonian expansions, they're also written in this factorized form. And having the radiation, one can compute energy and angular momentum in the radiation, and then use energy balance to get the back reaction on the orbit and continue the evolution in this way. So then finally, the full waveforms of effective on-body. So far, I've only described the inspiral part, but once the inspiral is computed and reaches the so-called light ring in EOB, which is a peak in the orbital frequency, then one makes a smooth transition to the perturbed final black hole, which is described at late times by a damped quasi-normal mode frequency, at least the gravitational wave signal. So it's easiest to look at the frequency evolution over time. So initially it's given by solving the Hamilton's equations for the effective on-body evolution. Once it reaches the light ring, there's a smooth transition that at late times goes to the least damped quasi-normal mode frequency. So finally, one can, of course, wants to test how well do these EOB waveforms work. And firstly, one can compare the model without doing any calibration to numerical relativity, so including only analytical knowledge. And then one gets the upper plot shown here. So in blue is the numerical relativity result, zoomed in now on a few orbits before the merger. The waveforms were much longer, and initially they were aligned, so they agree. But here then we see at the end there are some differences between the waveforms. But you know, it's not, the waveforms aren't completely off. But of course, this is not good enough for data analysis. So one has to calibrate these extra coefficients that were added in the EOB model. And with a calibrated model, comparing it then to some waveform that it was not calibrated against, then one finds relatively good agreement, at least in this example shown here. And yeah, of course, this has to be tested over a wide parameter space and so on. This is probably, yeah, so the agreement can look a bit different, but in principle, one can generate waveforms over the entire parameter space, but they have only been tested against numerical relativity in a more limited corner of parameter space. Okay, so spins can also be included in this model. Then it gets even more complicated, because then the spins introduce some subtleties which are treated in different ways between different approaches, even within the effective on-body model. But it has also been developed. One approach uses the test mass limit in Kerr, which is the so-called TOB resum S models by Damour, Nagar, and collaborators. And the other approach uses the test spin limit incur, which is the so-called SEOB-NR models by Alessandra Bonanno and her group and collaborators. All right, so this is what one would need for black holes. Of course, there could be more improvements to the models, but we also, to test aspects of general relativity, we would also like to test black holes. So we would also need to have some idea of what changes when in the waveform when the object is not a black hole. And yeah, maybe just to say before I go on, there are many models now available. Different groups are producing different models because it's, of course, so important to have good models, especially now that the data quality is getting better. So going back to what changes for objects that are more general than black holes. So you will also hear a talk by Nayesh Afshordi about after merger, what could change, but I want to also focus on what can change in the inspiral for the progenitor black hole-like objects. And the inspiral is useful to look at because their effects are relatively clean and they accumulate over many cycles of the waveform. And they are the differences of a black hole compared to other object waveforms are not so large, but they are due to some very generic phenomena. The first one is spin-induced multipole moments. There's also an effect due to the fact that a black hole has an event horizon, whereas other objects might have a surface. And then there are various kinds of tidal effects. Those can be either resonant excitations or even non-resonant excitations, which means just global deformations without any oscillatory behavior of the quasi-normal modes of the object. And that's, of course, really interesting because it enables a spectroscopic study of the object. Now, all of these effects are generic, but for each of them, there are certain characteristic parameters associated that, first of all, set the size of the effect in the waveform to some extent, and also depend on the internal structure and the nature of the compact object. So let me give you an example of such a parameter, which is called the tidal deformability. So let's think of a spherically symmetric object, so it's non-spinning in isolation, but when it's placed in a binary system, then it responds to the tidal field due to the space-time curvature of the companion by deforming in general. And in the limit that the variations in the tidal field are much faster than any internal time scale of the object, then the induced deformation that is imprinted in the exterior spacetime of the object. So when a general object deforms, then in general, except in special cases, also that will change the exterior spacetime away from spherical symmetry. That mapping between deformation of the spacetime and of the object itself is highly nonlinear in GR. But for gravitational waves, we need to focus on the spacetime. And in this adiabatic limit, the deformation is proportional to the tidal field with a proportionality coefficient that is the tidal deformability parameter. And this is 0 for a black hole. But for other objects, it is generally non-zero. And to compute this tidal deformability, one has to solve the Einstein field equations and energy momentum conservations and understand how does the object respond to tidal perturbations. And this can be done. And the example case where this is most used is for neutron stars. where there are still many open questions about all the microphysics of the dense matter in the interior, which is compressed by gravity to several times the normal nuclear density. So completely new forms of matter emerge that we don't encounter anywhere else in the universe. And as a result, we still have many models of the matter shown here in terms of the pressure density relation. And given such a model of the matter, one can say what is this tidal deformability parameter for a given mass. And you see on the right that the curves of deformability versus mass change depending on what matter model you pick. Now, this is not only limited to neutron stars, one can also examine other objects, for example, boson stars, which are condensates of self-interacting scalar fields. And what you see in this plot here is again a measure of deformability versus mass. And in purple, you see an example neutron star curve, whereas the other colored line are different boson star models. So these are just some examples that illustrate how information about the nature and interior structure of the object is encoded in these tidal deformability parameters, which are in turn imprinted in the gravitational wave signals. Now, to describe the imprints in the gravitational waves, we also want to have a slightly more realistic description of the tidal effects. Because so far I've only told you about this limit where timescales are very different, but in reality, that is a very restrictive assumption. So we would like to not make it a priori, because a general object has a rich spectrum of quasi-normal oscillation modes. And if some have frequencies lower than a kilohertz or so, they could potentially be tidally excited in an inspiral. Higher frequencies could potentially be excited for non-circular inspirals, but let's say for circular inspirals for now. And this is because from the point of view of the object, the companion is orbiting around and exerting a tidal force that changes on the orbital timescale. And then as the orbit shrinks, the tidal force sweeps up over a wide range of frequencies, so that might excite a resonance with an internal mode, or even a non-resonant excitation can lead to a significant effect. So this is the case with the fundamental modes, which correspond exactly to this deformation I've described to you before, just a global deformation that is, at least in circular inspirals, not fully resonantly excited. So there's no visible oscillation, but nevertheless, there's an enhanced tidal response, which is shown in the plot here. So the plot shows the tidal response versus frequency. So the inspiral goes from left to right here. And the more realistic response is the solid line that takes into account that there's some approach to a mode resonance, but it's a very broad resonance. It's quite enhanced compared to the strictly adiabatic limit. But this response is not only affected by the properties of the object itself, of the matter or whatever makes it up, but also by relativistic effects like the redshift and the frame dragging, also by spin effects, both the spin of the companion and the spin of the object itself, and so on. So it gets actually quite rich. Now, to describe this and incorporate it in our models that we use for data analysis, one has to think now, what is the effect of having a deformed object in a binary system? And if we're thinking in the limit that the two objects are widely separated, then we can describe the extended object basically as a center of mass worldline with additional multipole moments. And the multipole moments are things like the mass, spin, and these tidally induced moments. And here we are working to linear order in the spin, so we don't have the spin-induced moments and so on. But this gives you a general idea of the approach. And then one can write down a Lagrangian that describes the system in an effective way, which first of all takes into account that the extra effects that come in that are beyond the point particle approximation are that the tidally induced multipoles interact with the space-time curvature of the companion. There's also some Coriolis effects if the object is spinning. There are frame dragging effects, as I mentioned, due to the GR and spin effects. And there are also some internal dynamics of the tidally excited multipole moments. As I said, they correspond to the quasi-normal modes, so they behave as harmonic oscillators, except it looks a bit different because there are some relativistic generalizations and some tensor indices still floating around. And then having worked out this general effective action, one can actually substitute for what these fields are, what the redshift is, and so on, and then map the results to the effective one-body framework. But at this stage, we still have all of the multipole moments as dynamical degrees of freedom. But in the effective one-body model, it's more efficient to not have all of the dynamical degrees of freedom added to the model in a canonical framework, which doubles the variables because one has to go to the phase space description. So instead, what we do is to have some effective deformability parameter, which describes the enhancement due to the dynamical tidal effects. And it is obtained by solving for these dynamical multipole moments in an approximate way, so that in the end, we can map the two-body problem with an extended object to some effective problem, where the effective space-time potentials now also have some tidal corrections that approximate the dynamical tides. Other models of this are also available for data analysis. And then we also test the resulting model against numerical relativity. So this leads me already to the kind of final words here. So it gave you an idea of how more realistic physics can be included in these modeling frameworks, and what the framework is a priori. Now, of course, there are still some sources of inaccuracies and limitations of the models. So one kind of uncertainty is quantified by taking different waveform models, for example, the effective one-body model and the phenomenological approach. So this is also why it is so important to have different approaches to waveform modeling. So one can try to quantify the systematic uncertainties in the measurements due to these modeling choices. And then, of course, there's still a lot of missing physics in the models that needs to be included for the future. So far, at least as far as could be quantified, the modeling uncertainties seem to still be subdominant compared to the measurement uncertainties, but they are starting to become noticeable, but not yet really noticeable in some cases. So one case is shown here. Maybe if you look on the right plot, it's easiest to see, which shows the posterior probability distribution for the mass ratio for one event called GW 190412. And the different colors are different waveform models used for the data analysis. And you see that the distribution shifts a bit depending on what waveform model is used. But it is not yet, there's still, if you look on the left, one can also see the 90% intervals shown as these vertical lines. So there's still some significant overlap between these 90% credible intervals, but this is what was found. But in the future, now for the next observing run, which will probably begin near the end of this year or so, then LIGO and Virgo are supposed to be close to their design sensitivity already. And will also, together with KAGRA in Japan, will make more accurate measurements of nearby sources and also give us a much greater number and diversity of events. So this is, of course, really exciting. There's already plans for the next decade to have next generation ground-based detectors that will really take the next step towards precision physics and observe order 100,000 binary detections per year. There's also, of course, the upcoming space-based detector, LISA, which is already scheduled by the European Space Agency with some help from NASA to be launched in the mid-2030s. And that will open an entirely new window onto new classes of sources that are not accessible with ground-based detectors. So exciting prospects coming up to really do precision studies with gravitational waves and make many new discoveries, but to really maximize the science gains and take full advantage of all of this upcoming data, one also needs advances in the modeling to make sure that models are very accurate over a large range of parameter space, include the relevant physical effects, also have some means to test GR and black holes and beyond standard model physics, in addition also to the dense matter physics of neutron stars. And you will hear in the next talk a bit more about that to test GR, what is needed is also examples of what waveforms could look like in modified theories, in addition to current methods that are based on adding parameterized deviations to waveforms, and so on. So there's a long list. This is not complete, but there's still a lot of work to be done. But nevertheless, in conclusion, gravitational waves are an exciting new field. We have learned a lot in the last years with the many observations of binary systems. One has to keep in mind that our interpretation and measurements do rely on the theoretical models. So analytical modeling has made a lot of progress on various fronts, and also has to be used in synergy with numerical relativity to really build full waveforms. But some of the key roles of using analytical approaches is that one can identify characteristic parameters such as the tidal deformability parameter. One gain deeper insights into the physics, and one can establish a link between high energy theory and gravitational wave experiments. As I said, there's a potential for many new insights with upcoming data, but yeah, as I already mentioned, there's also an urgent need to simultaneously advance the modeling to make sure our interpretation is robust, that we don't miss interesting new kinds of signals or effects, and also to act as a pathfinder for the science case for the future detector plans. So with that, I would like to thank you very much and be happy to take any questions.